Right now, this iPhone camera is looking at everyday objects, and a YOLO model is identifying them in real time. Watch what happens when I disconnect the phone from cellular Wi Fi. The predictions continue. No image is being sent to a remote server, and the result is not coming back from the cloud. The model is running here on this device. That is the basic idea behind Edge AI. In this video, we will build a clear mental model of Cloud AI and Edge AI. Look at a real offline demonstration and then examine where Edge AI helps and where it does not. I am Yogesh Shankar, an engineer working in Edge AI. Let's begin with what normally happens when an AI feature uses the cloud. A camera, microphone, or sensor first captures data. An application prepares that data and sends it through a network to a data center. A trained model runs inference there. Inference simply means using a trained model to make a prediction. What object is this? What word was spoken? Is this measurement normal? The server sends the result back and the application responds. This arrangement is powerful. A cloud data center can provide large processors, scalable storage, centralized updates, and models too heavy for a small device. Cloud AI is not the problem. The important point is that the network becomes part of the system. The total response now depends on connectivity, transfer time, server availability, and the cost of moving data. Edge AI changes the location of inference. Instead of sending every input to a distant data center, the model runs close to where the data is produced. The edge could be a microcontroller, a camera, a phone, a vehicle computer, a factory gateway, or even a local server. The device does not have to be tiny. What matters is that useful intelligence happens near the source of the data. Also, notice one important distinction. A model may still be trained in the cloud and then deployed to an edge device. So, edge AI does not necessarily mean that the cloud disappears. It means that the device can perform the required inference locally without making a cloud request for every prediction. Now, let us return to the demonstration. This is the official Ultralytics YOLO app running the bundled YOLO 26 Nano object detection model. The app uses Apple's Core ML framework to perform inference on the iPhone. Camera frames are processed locally, and the app draws a label, a bounding box, and a confidence score around each detected object. This iPhone is the edge device in this demonstration. The important point is that inference happens where the camera data is produced. I will show it several everyday objects. The model knows their classes, but it has not seen these exact physical items. Here is a water bottle, now a cup. The table appears as another class. We can see the labels, boxes, and confidence scores change as the camera view changes. Now, I will enable airplane mode and make sure Wi Fi is also switched off. The app continues to process new camera frames and produce predictions. I can even force quit it and reopen it while the iPhone remains in airplane mode because this nano model is bundled with the app and inference runs locally through Core ML. That proves something specific. This inference path does not depend on an active internet connection. It does not prove that the system is automatically private, accurate, or better in every situation. Those properties depend on the complete design, but it does show that the core prediction can happen at the edge. Why would we choose this design? The first reason is latency. A local system can avoid the round trip to a remote server. For a safety alert, an industrial inspection, or an interactive feature, reducing that delay may matter more than using the largest possible model. The second reason is data locality. A camera or microphone can process raw input locally and transmit only a result, an event, or a carefully selected sample. That can reduce exposure of sensitive data. But local processing is not a privacy guarantee. Storage, logging, security, and access control still matter. The third reason is reliability. If a product must continue operating in a tunnel, a remote field, a factory with restricted connectivity, or simply during a network outage, local inference can preserve imported functionality. The fourth reason is bandwidth. Video, audio, and high rate sensor streams are expensive to transmit continuously. Processing them near the source can reduce network traffic and cloud cost, especially when only a small fraction of the data contains an event worth sending. But moving AI to the edge create constraints. The device may have limited compute memory, energy, and cooling. A model that works completely on a data center GPU may be too slow or too large on the target hardware. Engineers may need quantization, pruning, smaller architectures, or specialized accelerators. Every optimization can affect latency, power, and accuracy, so the system has to be measured on the real device. Updates also become more complicated. A model deployed across many devices needs versioning, monitoring, secure delivery, and a recovery plan. And some tasks genuinely belong in the cloud because they need very large models, broad context, and frequent updates or aggregated information. This is why the useful question is not, is edge better than cloud? The useful question is, where should each part of the intelligence run? A practical decision starts with five questions. How quickly must the system respond? Can the raw data leave the device? What happens when the network fails? How much data would we need to transmit? And what compute, memory, and energy are available locally? If the answer demands immediate response, local operation, or reduced data transfer, edge inference becomes attractive. If the task needs enormous models or centralized knowledge, the cloud may be the better choice. In many real systems, the strongest architecture is hybrid. Immediate decisions at the edge and heavier analysis, training, or fleet management in the cloud. So, can AI run without the internet? Yes. A trained model can perform inference entirely on a local device, as this demonstration shows. But good edge AI is not simply about removing the network. It is about placing computation deliberately close enough to the data to meet the real requirements of the system. I am Yogesh. If you value practical explanation built from first principles, subscribe. And tell me in the comments what edge AI system should we examine next.